Let's record some 6.1, day 1 and day 2. So first on number 1, the idea is you start off with 120 degrees and you want to get 4 angles that are coterminal, that stop at the same place. So you can take 120 degrees and add 360 degrees. That's a wasted revolution. When you do, you get 480 degrees. So that is coterminal to the original. If you add another 360, you get 840, which is also coterminal to the original because you've added a second wasted revolution. So these three are all coterminal. If you wanted to start off with 120 and subtract 360, you take away a wasted revolution and get to negative 240. So these would stop at the same place. And then if you subtract 360 again, you get 600 degrees. And so all of these angles are coterminal. We do something similar over here, where if you want to get a coterminal angle, you can either add 360 as many times as you need, or you can subtract 360 as many times as you need. Then, in number 9, we're wanting to change 150 degrees into radians. And what we're going to do when we're changing from degrees to radians, or radians to degrees, is to multiply by a well-chosen 1. And so the well-chosen 1 we're going to multiply here, we need to think about either taking away degrees and have them cancel out, or we're going to introduce degrees on top when we already have radians. So here, since we already have degrees, to take 150 and turn it into radians, I would multiply it by pi over 180. And since pi is equal to 180, this is the same thing as multiplying by 1. So these cancel out and give me 5 over 6, and the pi is just left there. To be clear how we got that, I rewrote this as 30 times 5, and this as 30 times 6. So the 30 degrees canceled out and leaves me with 5 pi over 6. In a similar way, I take negative 60 and turn it into radians by, again, multiplying it by pi over 180. How did I know if it was pi over 180 or 180 over pi? Well, here I want to get rid of degrees, so I put degrees on the bottom. But this thing is just equal to 1. So when I multiply, this thing will look different when I multiply by 1, but it will still be equivalent. I rewrite 180 as 60 times 3. The 60s cancel out and give me negative pi over 3. And remember, there are those angles that we need to know by heart. Let's go ahead and put those here just to remind ourselves. Take a second and recall that 30 degrees is pi over 6, very good. 45 degrees is pi over 4. 60 degrees is pi over 3. And 90 degrees is pi over 2. Because every time we're thinking 180 divided into how many parts gets us this angle. So those are ones that you need to have memorized. So I'm going to say must memorize these right here, because we're just going to use them so much. It just helps you if you have them memorized. So I think this last one is similar. When I go here, I've got 2 pi over 3. And again, the idea is that I would like it to turn out to be in degrees. So since my original thing does not have any degrees in it, I want to introduce degrees. So if I want to introduce degrees, I put it on top. So 180 degrees over pi, this thing, again, is just a well-chosen 1. It's just equal to the number 1. So when you multiply by 1, it's not different. It just looks different. So let me go over here. This should be, I think that's purple, yeah. So here, the pi's cancel out nicely. And then 180 divided by 3 is 60. So it ends up what you're left with is 2 times 60, which is 120 degrees. Again, here, if you have this and you multiply by a well-chosen 1 to introduce degrees, I put 180 on top since it's already radians. When you introduce degrees, you get what you need, and we move on from there. Cool. All right. 15 is exactly the same. If you're going from radians to degrees, you're introducing degrees, so you multiply by 180 over pi. If you're going from degrees to radians, you divide by 180 to cancel out degrees. So you're always thinking, do I need to introduce degrees to radians, or do I need to cancel out degrees if you start with degrees? All right, so in this question on 29, it looks like they gave us an angle of 4 radians, which opens up like this, because we remember that about 3 radians is half a circle. So 4 radians is going to be more than 180 degrees, so it should look something like that. If that's our theta, and we want to know r if we've opened up an arc length of 10 centimeters, then I must have memorized the formula S is equal to r theta. Must memorize. It's just really good to know, right? Memorize. Must memorize. S is equal to r theta. And then remember, caution, theta must always be in radians. I think that that's really important to remember. So I'm actually going to put that here again just to make sure that you see it. Let me come over here and go copy. Let me move this 31 right here. That's fine. But over here, I really want to make sure you see that for this one, 29, theta must be in radians anytime you use that tool. So if S is equal to r theta, theta must be in radians, because the way we thought about arc length, it was a radius multiplied by radians. So if we plug in 4 for our radians and 10 centimeters for arc length, when you divide, you end up getting 2.5 centimeters must have been what the radius was. Which makes sense. If I walked around if I walked around 10 and my radians were 4, then that means I walked around about 4 times. And so that's why we have that, or exactly 4 times. Here, if I open up 45 degrees and I know R is 8 centimeters, I want to find out what the arc length was here. So what is this arc length S? That's what I'm trying to figure out. S is equal to question mark. Well, again, S is equal to r theta. So I cannot, here's the common mistake, people will put degrees in here. But remember, arc length is radius times radians. Arc length is radius times radians. So I'm going to put my radians here because 45 I have memorized as pi over 4 times my 8 centimeter radius just gives me 2 pi centimeters, so it's approximately 6.28 centimeters. Well, then if I want to know the area of this section right here, the area is equal to 1/2 r squared theta. Well, again, I put in my radius, which I know, and I put my radians in. I end up getting 8 pi centimeters squared, or about 25.13 centimeters squared. Why is it centimeters squared? Because when we plugged in 8 centimeters, we squared it to get centimeters squared. And that makes sense because it's area. 33. If they give us a radius and the arc length, I guess we could find theta. We could find out how much of an angle did we open. What is this theta? So if this is 4 and I've walked 7, I know it's got to be, you need to have some idea how many radians it should be. Well, we know if we walked, for example, 8 out here, then that would be laying out 2 radii on the outside, and so the angle would be 2 radians. Well, now, since we've only opened up 7, we know that this has got to be less than 2 radians. How many radians is it? Well, if S is equal to r theta, and that theta must always, again, be in radians, then 4 here, 7 here, notice they're both centimeters, so when you divide, the centimeters cancel out, and I get theta radians, because again, radians are unitless. So 7 over 4 is how many radians we had. And if you want to know what that is in degrees, 7 over 4 radians has no degrees, so we must multiply it by 180 over pi to introduce degrees. Remember, this thing right here is just a well-chosen 1. So then from there, I guess 180 divided by 4 is 45. And then to do a little mental math, I thought this was a great chance to practice that. 45 times 7 is just 40 times 7, which is 280. And 5 times 7, which is 35. So when we add them together, we should get 315. So 315 over pi is about 100.27 degrees. If you go to a decimal, you must put squiggly equals, because this decimal goes on forever. So when you divide, its decimal also goes on forever. To find the associated area, we must use radians, and A is equal to 1/2 r squared theta. Again, we need to memorize that, since it's something we've used a couple times. We can put the radians in here, and the radius here. Remember, this is centimeters, so when you square it, you get centimeters squared, and we get 14. All right, 35, which looks like it's going to be the last one here. If they give us 50 degrees and 8 meters, the common mistake is to just start plugging things in. But more importantly, notice they gave us the diameter was 16 meters. So the radius is half of that. It would be 8 meters. But also, if we're now going to find the arc length, theta must be in radians, because arc length is the radius times the radians. Say it with me. The arc length is the radius times the radians. So if I take that 50 degrees and multiply it by pi over 180, that's my well-chosen 1. It's going to make it look different but be the same. I'm going to see that these zeros cancel out, because you can divide them both by 10. That's why we get 5 pi over 18, which we put in here. And then if the radius is 8 centimeters, when you multiply, you get 20 pi over 9 centimeters is how long this arc is. If you would like to now know the associated area, then you must know the formula. A is equal to 1/2 r squared theta. You can plug in the radius and the radians and get 20 pi over 9 centimeters squared for the area. That's interesting. Would I expect that to work out the same? Would we expect that to work out exactly the same? That's 64. That's 8. Yes, we would expect it to work out the same. Wait. No, because I did that wrong. That's 64 divided by 2. That should be 32. Should be 32. So be careful there. So this is going to end up being, when these cancel out, that's going to be 32 times 5 pi over 18. That's going to be 160 over 18 pi, yes. Take a, let's take a, I'm going to take a 3 out of both those. 160 divided, that's not going to be divisible by 3, because when you add the digits, what you get is something that's not going to be divisible by 3. They're both divisible by 2, so that's just 80 over 9 pi centimeters squared. Yep. And I will double check that for you. But that should be what we end up getting. So let's look at it one more time just to make sure we're on the same planet. So 8 squared is 64. And we've got 5 pi over 18 and 1/2 out front. This divided by this is 32 times 5 pi over 18. 32 times 5 is 30 times 5, which is 150. And 2 times 5, which is 10. So we should get 160. That's the mental math that got us this. Then we said, hey, there's a 2 in both. That got us this. Wonderful. And that's all for part 1, day 1, I mean. Let's move on to day 2. Let me go back just a little bit for you. When we look at day 2, same sort of deal before. The idea, if you're trying to get coterminal angles, is you either add 360 or you are subtracting 360. Each one of those is just a wasted revolution going either clockwise or counterclockwise. So that's how we get all those. Just make sure you didn't screw up any easy math. Now, here's where it's interesting. What if I have this angle, 5 pi over 6, and I want to know something coterminal? Well, now a wasted revolution is going to be 2 pi, because that's the same as 360 degrees. So when I add 2 pi, sometimes 2 pi is pi, but sometimes it's 12 pi over 6, especially if I'm wanting to add it to something that has over 6 in it. So now, this would be a wasted revolution. So when I add these, I get 17 pi over 6. If I add another wasted revolution, or in other words, a 2 pi, which is 12 pi over 6, I end up getting 29 pi over 6. If I subtract a revolution, again, I'm subtracting 12 pi over 6 because my stuff has over 6 in it. All right. All right. Let's see what we've got here. Okay. To get a as a function of theta, I must remove r. So it says, look what you got here. It says what you've got is you got this s, which arc length is 8, yeah? And it says, can you please write the area as a function of only theta? Well, first thing I do is I say, look, I have this memorized as the area formula for a sector. So that's going to be the area of this sector. And notice it has an r and a theta in it. So to get a as a function of only theta, I guess I have to remove this r somehow. And here's how I'm going to do it. Since s is equal to radius times radians, then since s is 8, I now have a relationship between r and theta. So I can solve for r as 8 over theta, and so now I can plug it in right here where our old r was. You end up getting that the area is equal to 32 over theta. Yes? So notice what's super interesting here is we're saying if you fix the arc length, but you let this theta get bigger and bigger, the area actually gets smaller. Because what we're saying is you have this huge, imagine a really, really big angle, but you keep this the same size every time, yeah? So imagine we have this huge angle, but we only have 8 across of it. Then what that's going to do is that's actually going to make that area get smaller and smaller every time, which is pretty cool. Okay, so 42 is a problem, not an exercise. So let's see the setup. It says you have a hexagon, a regular hexagon, I think they were implying, inside of a circle. When you do, you're going to get some area that's left over on the outside. And they tell you that that leftover area is 24 centimeters squared. The reason I do this is because it's in the ballpark of a very hard SAT type problem. Often the SAT might have a question where you are taking out some area. So this is a pretty mature version of one of those questions. So here's all this leftover area. They tell us is 24 centimeters. And they want to know, what does the radius of this thing need to be? Well, I know first off from the area of a sector that this must be true. So, how did I write that one? So the area of this entire sector right here, the area of that entire sector turns out to be pi over 6 r squared. Because if you have 6 of these things, if you take 2 pi and divide it into 6 equal pieces, well, let's think about it this way. 360 divided into 6 pieces. Each one of these is going to be 60, but I have memorized that 60 is pi over 3. So that means this little angle right here is pi over 3. So the area of this sector is going to be pi over 3 times whatever the radius is squared. Right? That's what we're saying right here. Now, another thing to notice is we have all this leftover area out here. If we divide it into 6 equal pieces, I can find the leftover area just for one little sector when I cut out this equilateral triangle. So this little leftover piece right here is 24 divided by 6, which is 4. So since an equilateral triangle's area is going to be r squared since the equilateral triangle's area is r squared square root of 3 over 4, you would have to be given that, by the way. That means the area of the sector is going to be the equilateral triangle plus 4, that little bit that's left over. Well, guess what? We just said up there that the area of the sector was pi over 6r squared. The area of the equilateral triangle we just said was this much. And then that plus 4 is that little bitty green part that's added on. So now I have one equation with one unknown. And I just solve it for r by moving everything over to this side, factoring out the r squared, and then dividing. So I'm really close here. Since I have r squared, I just take the square root of both sides. And I get plus or minus the square root of this. But we know the radius must be positive, so it turns out to be approximately 6.645 centimeters. Okay. Again, this is a problem, not an exercise. I would not expect to see something like that on a high-stakes test, but it's important that we really push ourselves to go back, look through that problem, and see if you can understand it. Okay. That's 42. Now 43 and 49 are ones that could be test-able. So we've got a windshield wiper, and notice here's the wiper, and it wipes through a distance here to create an area. This part down here does not get hit by the windshield wiper. And here's what we want to know. We want to know what percent of the entire windshield gets wiped if, well, first off, we know that the total area of the windshield, is 54 by 26, 54 by 24, excuse me. And a 54 by 24 is 1296. That's going to be the area of the whole thing. And so we're going to take that as our denominator, and whatever we get for just the wiper parts is going to be the numerator if we want to find the percent area. So how do we find the area of just this wiper part? Well, can you see that it's the area of a sector? So we're going to take the area of this sector. We're going to have to subtract off the area of this sector down here. Again, an SAT type problem. We have one area and then you cut out another area. So this angle, they tell us that the wiper moves through 120 degrees. Well, when I multiply that by pi over 180, I get 2 pi over 3. That's how many radians the wiper moves through. The wiper is 17, inches? We'll say it's inches. Look in the book. It's 17 inches long, and this, from the point here where it rotates, the pivot point, then to the bottom of the actual blade itself, is 5 inches. Now, if I want to find the area of the entire triangle, I take 1/2 r squared times theta. Well, this whole distance is now going to be my radius if I want the whole area, and 5 times 17 is 22. So the area of the entire thing is 1/2 22 squared times 2 pi over 3. So we end up getting this as the area of the whole thing. Well, if I want the area just that the wiper has cut out, and notice the little symbol I give it one of these Deweys. It's got the bottom cut out. It's the area of the whole thing minus the area of the bottom, minus this little green Dewey down here. But the green Dewey down there is 1/2 its radius squared times 2 pi over 3. Because this one is just 5 long, and it cuts through the same angle of 2 pi over 3, its area is 1/2 r squared, 5 squared, times 2 pi over 3. So when we subtract these two suckers, we get 459 pi over 3. That's going to be the area of just the blue part where the wiper moved through. So that divided by the total area of the windshield gives us 0.371, or approximately 37.1%. Cool. Then 49. This is a classic things are rotating. And here's the main idea we need to think of. Let me put a big old red box around this. This is the big thing to realize, is that linear speed, s over t, is equal to the radius times your angular speed. So how is the arc changing over time? It's equal to how is the angle changing over time if you multiply that by r. So here's what we have. We have a spinning compact disc, CD. You can think of it as DVD or Blu-ray if that makes it easier. And then 5 centimeters, 5.7 centimeters away from the center, we have something rotating at 200 RPMs, rotations per minute. Excuse me. Well, first, let's understand that in terms of radians. Well, if my angular speed, theta over t, is 200 rotations every 1 minute, well then if I use a well-chosen one to introduce radians and cancel out rotations, 2 pi radians is equal to 1 rotation. And these cancel out just like I do in chemistry, change my units. I get 400 pi radians every minute. So that's my angular speed in terms of radians. So remember, my linear speed, s over t, is just equal to, well, s I have memorized as r theta. If I pull out that r, I get that my radius times my angular speed is just my linear speed. Well, my radius, it said, was 5.7 centimeters. And my angular speed, I just found out, was 400 pi radians a minute. So when I multiply it together, notice radians are unitless, so they kind of go away. And I get centimeters over minutes. So this is what my linear speed turns out to be. 2,280 pi centimeters every minute is the linear speed of that dot. Bloop, bloop, that dot right there. Then if we do C as in cat, here's the important thing to notice. Why is question C super interesting? We need this one big key fact. And maybe I make it a different color so it's really obvious what I'm saying here. Here, maybe we go green. Linear speed at any point is the same. So remember, this is our angular speed. Radius times angular speed. Then we already know that this is our linear speed. It's equal to the radius times the angular speed. And so we divide that 3. We end up getting that theta over t is equal to this. So if you're 3 centimeters out, then your angular speed is going to be this, right? But if we want it in revolutions per minute, that's in radians per minute, we would have to take this and change our units by multiplying it by 1 revolution every 2 pi radians. So our radians cancel out, even though it's unitless, we get revolutions per minute. Then over here, again, it's important to memorize that linear speed is equal to radius times angular speed. So if this is our linear speed, and I want to know at some point on that CD, r units away from the center, what is its angular speed? We divide by r, and we get that this is its angular speed. multiplied by a well-chosen 1, we get 1,140 revolutions every r minutes. Cool. Hope that helps just a little bit. These are not easy, but the main thing to think about these, two things happen in these sorts of questions. First, you must know this idea that linear speed, how does arc length change over time, is equal to angular speed times the radius. And then we just have to do some unit conversions. Let me know how I can help you. Talk to you soon.